So just to get vocabulary to be the same, make sure we understand what we're talking about when we deal with angles. Let's make sure we know that in a coordinate plane, an angle is one in what's called standard position when the vertex coincides with the origin. So that's the vertex on the origin. Vertex is like the elbow of the angle, so it bends, turns the corner at the origin. And what's called the initial ray coincides with the positive x-axis. So if we look at this image we have here, there are many angles here, 1, 2, 3. I mean, we can make up whatever angles we want, but as long as it has a vertex at the origin and starts at that blue angle that I've highlighted, it is going to be in what's called standard position. The other ray in this image is going to be called the terminal side. Terminal meaning like end, so we end at the other ray. So in this image, angle COB is in standard position with an initial side of OC and a terminal side of OB. So we see that it has a vertex at the origin, starts at the blue line at the initial side, OC, and ends at OB. On the other hand, if you found the angle DOB, which is from here to the origin and up, that is not standard position. That's still technically an angle. It's a valid angle, but it's not in standard position because this initial side is not on the x-axis, the positive x-axis. Pretty much all of the angles we'll deal with in this class will be in standard position, especially when we get around a unit circle and we talk about periodic motion. It always starts at the initial side. Now we can have positive and negative angles. A positive angle measure indicates rotation from the positive x-axis in the counterclockwise direction. Counterclockwise, like a clock goes opposite, counterclockwise is this way. If you see that your angle is measured in the counterclockwise direction, it is a positive angle. So this angle here in the picture, alpha, is a positive angle. A negative angle is going to rotate the opposite direction. So a negative angle starts at the positive x-axis but goes in a clockwise direction, which is this way, like a clock. So the angle in this image, beta, is a negative angle because it goes down and around instead of up and around. Does that make sense? And we will have both positive and negative angles. One more piece of vocabulary from geometry you just need to make sure we remember. The word coterminal is actually very helpfully named. Co meaning together, terminal meaning ending. It means two different angles end at the same ray. They differ by an integer number of revolutions, or in more simplified vocabulary, circles. So in this image here, we have alpha, which is some acute angle, and we have beta that goes all the way around the circle and then up and ending at the same ray as alpha. So alpha and beta are coterminal angles. Together they end at the same ray. Does that make sense, that vocabulary? Now this part that says by an integer number of revolutions, that just means that you will take like 1 full circle or 2 full circles or 3 full circles to meet at the same coterminal angle. To measure the amount of rotation in an angle, you are likely familiar with the use of a protractor from geometry to measure in degrees. But in AP Pre-Cal, we are not going to be using degrees. We're going to be using a different unit of measure for angles. The unit of measure for angles that we're going to use is called a radian. Notice that is not radius, it is radian. A radian measure of an angle in standard position is the ratio, so a fraction, of the length of the arc of a circle centered at the origin subtended by the angle to the radius of that same circle. Whoa, that was a lot of words. Let me show you what I mean. This angle theta, which is going to be in your image right here, theta, is found by taking the arc length, which is the distance surrounding the circle, like on the circumference, and dividing it by the length of the radius for that circle. So theta, the angle, is the ratio of the arc length, the curved distance divided by the flat distance of the radius. Instead of measuring 1/360th around a circle, which is a degree, we will be using radians to talk about our angles. Now, fun fact, and we'll be discussing all of these measurements over and over again all unit, but an angle with a measure of 2 pi radians, we need to remember this so much. An angle with a measure of 2 pi radians opens or rotates an entire circle. So if you think about this formula for circumference that you learned in geometry, the formula for circumference is 2 pi r, 2 pi times the radius. Well, 2 pi is the distance all the way around a circle. So the circumference takes an all the way around the circle, 2 pi radians times the radius itself to give you the circumference. That's where we got the 2 pi from. So question, if all the way around a circle is 2 pi, what's halfway around a circle? 1 pi, or just pi. What is only a quarter distance around a circle? Half of pi. So we would say pi over 2, so half of pi. What about if I go 3/4 of the way around a circle? 3/2 pi. So if this is a half, this is 2/2, this is 3/2. 3/2 pi. Very good. So we're going to be dealing with fractions when we talk about what in the previous classes you used as degrees. We're not using degrees anymore, we're using radians, which also means don't put the little circle symbol for degrees. We're not measuring in degrees, we're measuring in radians. It doesn't need a degree, it doesn't need anything around it. Does that make sense? Okay, cool. It is also important, eventually, we're not doing this really today because we're not getting any degree or radian measures. Your calculator, when it auto resets to radian mode. But I teach more than just this class, so when we pick up our calculators, you need to make sure that it is in radian mode instead of degree mode, because you'll get completely different answers whenever we start using the calculator for our trig functions. Again, when you reset it, it is in radian mode, so that's nice. But I teach other classes, and we will be switching those classes to degrees, so you need to make sure it's in radians when you pick up a calculator. Cool, so let's draw some angles in standard position that have the following angle measurements. And I'm actually going to skip part A for a second, and we're going to go to B and C because they're actually easier. In part B, it says to draw an angle in standard position that has pi radians as its measurement. Well, you guys just told me how far I should go around the circle to go pi distance. How far was that? Half. So what we're going to do is we're going to draw an initial side, a vertex, and our terminal side, and show that theta went all the way over here. That is our angle. It starts at the x-axis, goes to the x-axis. Halfway around an entire circle is pi radians. How would we draw pi over 3 radians? If that whole top was an entire pi, what should I do to get only a third of that? What I'm going to do is I'm going to take the top section here, the first 2 quadrants, and I'm going to split it as best as I can visually into 3 parts. Do we see how I have 1, 2, 3 parts that are, air quotes, equally spaced, because I know I just drew that and it's not perfect, but they are equally spaced. Well, if I want only 1/3 of that, when I'm drawing my angle, I would have my initial side, my vertex, and my terminal side. This would be pi over 3. That's our theta. Cool. So when you have a radian measurement that has the pi in it, it's really easy to graph because you're just taking a ratio of either a full circle, 2 pi, or of just like that top semicircle, which is pi. But for part A, it says to draw 0.5 radians. Now remember, a radian has to do with the measurement of the radius itself. So if we were to highlight just the radius itself, so like I'm just going to go here, and I know that that's going to get confusing when we do our initial side, but bear with me. That is a full radian because it's the same distance as the radius. I want half of that. So I'm going to estimate this much. this is half of a radius, right? Because it's half of that distance from the origin to the side of my circle. I want to go that same distance around my circle to draw my angle. We're going to estimate it because we don't have actual measurements here. You only want to move this much around the side of the circle. So if I was going to do this much around the side of the circle, I would estimate it to be about that looks pretty good. In my mind, those are pretty similar in length. One of them is bent, which is why we can't use a ruler to get it perfect because we're bending it around the circle. But if we use those two measurements to draw our initial side, our vertex at the origin, and our terminal side, this is a pretty good estimation of theta. Because the distance I've covered around the circle is approximately, because we're drawing it and we're humans, half of the radius of that circle. Because radians has to do with the radius of the circle. Those are two separate vocabulary words that mean two different things but are intimately related. I know part A was confusing, but for part B and C, did we follow how to draw these angles? Those are the ones I'm more interested in for us. Fabulous. Okay, so not only can we draw these angles, we can also use this standard position with a circle centered at the origin to talk about where these terminal rays intersect the circle on our graph. So given an angle in standard position and a circle centered around the origin, as pictured here, there is a point P where the terminal ray is going to cross that circle. In the images we drew, that was here, and here, and here. We can find all of those coordinate points around our circle. Now we're going to let that coordinate point P just be the x and y value, x and y for now. So hang on to this. It's just a regular coordinate point. But what's cool about this is that coordinate pair gives us the displacement of this circle. The x value in the coordinate pair gives us the horizontal displacement. Okay, horizontal displacement. I'll highlight the x in the same letter. What I'm talking about with horizontal displacement from the point on the y-axis is looking at this terminal ray. Let's say this is point P. This horizontal displacement is the distance if I were to draw a straight line back to the y-axis, no matter where it is height-wise. I'm just going horizontally over to the y-axis. This horizontal displacement will be positive when the point is to the right of the y-axis and will be negative when the point is to the left of the y-axis. Since on a coordinate grid, positive numbers are on the right and negative numbers are on the left. Continuing on, the y value in the coordinate pair is going to give us what's called vertical displacement, comparing the point to the x-axis. So in a quick little image here, what it would look like if this was my terminal ray, the vertical displacement is just the distance going straight down to the x-axis, no matter how high it is. Straight down. Vertical displacement, pretty obviously, is going to be positive when the point is above the x-axis, since those are positive y values, and negative when the point is below the x-axis. So that's the y value. I forgot to highlight y up here. So one of the things I'm going to ask you to do is describe the displacement of different points around a circle. And it is really easy because you're just straight up reading the coordinate points, but we are going to have to write sentences because it's pre-cal, so we're going to write in discussion form to talk about this displacement. So we can use the location of point P on a coordinate grid to measure these horizontal and vertical displacements. If we were to describe or determine these two displacements for this point P in example 2, it would be very simple. We said that the x-axis is, x value is your horizontal displacement, and the y value is your vertical displacement. So the sentence we would write here to answer this question is, we would say the point P has a horizontal displacement of 2, because that's the x-coordinate, and a vertical displacement of 5. Easy peasy, yeah? Read the coordinates. They tell us our displacements. They tell us the distances we're traveling left or right and up and down, which is what coordinates do. But that's just the beginning, because once you have these displacements or these distances from your different axes, you're going to be able to compute or measure these displacements in terms of the radius length. So we're going to start creating some ratios, getting us back to the radius length in radians. Now, before we flip the page, there is one more piece of information we're going to need on the other page. We're going to need the distance of this radius. Now, unfortunately for us, this distance right here is not cute. We can't just count it on our coordinate grid. We're actually going to have to figure out what that radius is. What are some things we know about radiuses, though? Just give me anything we know about a radius.
Is half of the diameter.
Half of the diameter, cool. Fun geometry fact. What else? If this is the radius, what is this? Isn't this also the radius? And if I were to go this way, is that the radius? And if I were to go this way, is that the radius? So I can use any point along the circle and the origin to find the distance between them and get my radius. So if we were trying to find that radius length, we would need to do the distance formula, comparing the origin to the point. If you remember your distance formula from geometry class, that is the x value subtracted then squared plus the y value subtracted then squared. Now, since we're using the origin, you can pretty much see that the zeros are not really helpful. So this is 2 squared plus 5 squared square rooted. And if you throw that into a calculator, you would get that this radius length is approximately 5.385. If it was cute and we could have just counted on the coordinate grid, we would have done that, but we did not have cute numbers. Most of the time you won't have cute numbers. But we have now our radius length. We're going to need that on the other page. So anytime you have a circle, it's a good idea to just kind of keep in mind you might need to find that radius length just using the distance formula. Cool. Now we can flip over the page. Here's the meat and potatoes of today. Have 3 measures of ratios, comparing a displacement and the radius length that are going to become vital in understanding trigonometry. The first ratio we're going to have today is the ratio of sine. Sine is the sine of an angle is the ratio of the vertical displacement of P from the x-axis to the distance between the origin and the point P, aka the radius length. This is one of the formulas I'm going to need you to memorize. Sine of theta is equal to the vertical displacement of P from the x-axis divided by the radius length. Because we know some things about vertical displacement, sine is going to be positive when the terminal ray intersects the circle above the x-axis. And sine of theta is going to be negative when the terminal ray intersects the circle below the x-axis. Since we're using a vertical distance, up is positive, down is negative. So above the x-axis, you're going to get a positive number. Below the x-axis, you're going to get a negative number for this ratio. The value of sine of theta will always be on the interval between -1 and 0. We will refer back to that over and over again, so I don't need to explain it all that much. But if we're trying to find sine, another way I can ask you for that, like example 3 says, using the point P from example 2, which if you remember, P was 2, 5, what is the vertical displacement in terms of the radius length? Meaning, I want you to find what the sine of that theta was. What was the vertical displacement for this point P? Which one's vertical, the x or the y? The y, okay. And I'm going to divide it by the radius length. Now you might have to flip back over because it was a decimal. What did we calculate was the radius length for that circle? 5.385. Okay, in your calculators, what is 5 divided by 5.385? Round to 3 decimals, please. 0.929. So the sine of my theta, or the ratio between the vertical displacement and the radius length, is 0.929. Okay, flip the coin over. The second vocabulary word for today, another thing I'm going to have you memorized, is cosine. The cosine of an angle, which is another trig operation, is the ratio of the horizontal displacement of P from the y-axis and the distance between the point and origin, aka the radius length. This is another formula that might be on your formula quiz next class. Cosine of theta, by the way, one of my pet peeves is calling this cos theta. No, it's called cosine of theta. You're going to pronounce it correctly or I'm not going to listen to your question. Same with this. Don't say sin theta. That is sine of theta. Okay, please say it correctly. Pet peeve of mine. Okay, say it right. Cosine of theta is positive when the terminal ray intersects the circle to the right of the y-axis, because that means my horizontal displacement is positive. And cosine of theta is negative when the terminal ray intersects the circle to the left of the y-axis. The value of cosine, again, will also always be between -1 and 1. It has to do with how it looks when you're graphing it and moving around a circle. So again, we're still going to be using the point P from example 2, which was 2, 5. What is the horizontal displacement in terms of the radius length? AKA, what is the cosine of that theta? Okay, for this one, we want horizontal displacement over the radius length. What's the horizontal displacement here? 2. And my radius has not changed because we're using the same circle, so it should be the same radius the whole time. It's going to be 5.385. Beep, beep, bop. That's a calculator question. What do you get? The 4 of us who picked up our calculators today. 0.371, yes? Okay. That is sine and cosine. What's cool about the way we're learning this in this class is that it's tying in a whole bunch of things we've learned. We've talked about slopes of lines for a long time. We talked about the average rate of change for different types of functions, all the functions we've studied so far. And guess what? We're still talking about slope in this unit. We can measure the slope of the terminal ray. Since we know that the point and the origin are on the terminal ray, we can always fill in the slope formula the following way. This is the regular Algebra 1 version of a slope formula. y2 minus y1 over x2 minus x1. Well, if we just go ahead and do it where we're doing like, okay, this is x1, y1, and this is x2, y2. Actually, I'm gonna flip those around. We're gonna let this be the 2's and this be the 1's, so I don't have negative signs. When we fill in that formula, we would say y2, which is y, minus y1, which is 0. Okay, boring, subtract by 0. In the bottom, it would be x minus 0. Do I need to actually subtract by zeros? Which means that my slope is just the ratio of y divided by x. Now this y and x are coming from the coordinate point. So this ratio, the slope of my line, is going to be called your tangent function. Tangent function is the ratio of the vertical displacement of P divided by the horizontal displacement of P. But if you remember, vertical displacement is what we used when we did sine, and horizontal displacement is what we used when we used cosine. Their radiuses would cancel out since they're on opposite sides of a fraction, so really, tangent is just sine of theta divided by cosine of theta. And really, when we think about it, that means this is just y divided by x. Sine divided by cosine. So the letter you used in sine, which was y, divided by the letter you used in cosine, which was x. The radiuses would cancel each other out. Now tangent is interesting because it's not just all above, all below, all right, all left. Tangent, since it's a ratio of x and y, is going to be positive when both sine and cosine are either positive or negative. Because a positive divided by positive is positive, and a negative divided by negative is positive. And tangent of theta is going to be negative when sine and cosine are opposite signs. Since this is a ratio of numbers between -1 and 1, that ratio means that tangent of theta can be any real number. So we could get like a tiny little number or a huge number for tangent, and that's okay. It doesn't have to be between -1 and 1. So using, again, same point from example 2, which was 2, 5, we're going to find the slope of the terminal ray. Finding the slope of the terminal ray means that I am just really asking you to find tangent of theta. We said that tangent of theta would be the vertical displacement divided by the horizontal displacement, which is the same as sine divided by cosine, or y divided by x. 5/2 is a completely acceptable answer, but I can't help myself. This is a cute decimal, so we'll say it's 5/2 or 2.5. Both of those are fine answers. So we have our 3 trig functions that you might recognize as parts of a triangle. When you learned the 3 trig functions in geometry class, you probably learned SOHCAHTOA, which is opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. That's great if we were using a triangle, but we're already on a coordinate grid where we don't have the words opposite, adjacent, and hypotenuse available to us. They're the same concepts if you draw a triangle on these coordinate grids, but we can deal with the displacements on coordinate grids, which is a more advanced topic than just looking at triangles themselves. Now, last and not least, and you're going to see these words a lot, and I believe Mr. Chavez, if you had him for geometry, made you memorize parts of the unit circle. That's coming back to haunt you. The unit circle. I have a unit circle on my back wall. It's been up all year. You've probably politely ignored what it looks like. We're going to discuss what all of that means in the next couple days, and you're going to be able to fill in an entire unit circle by the time you're done with me, because I'm going to make it really easy. But when we're dealing with a unit circle, the radius of a unit circle is going to be 1. In the example we did today, the radius was 5.385, which meant we had to divide by a decimal number, and the numbers got even weirder with decimals. However, if I make my radius, or in multiple cases, my denominator 1, that means that sine of theta is the vertical displacement divided by 1, which really just means it's the vertical displacement. We don't have to divide by a number because the number we would divide by is 1. Same thing for cosine. It's the horizontal displacement divided by 1, but who cares to divide by 1? It's just the horizontal displacement. And again, because our radiuses would cancel out anyways, our radiuses are 1. Kind of boring. Tangent is still the vertical displacement divided by the horizontal displacement. These are also going to be something I'm going to have you memorize. I don't think I put them on the vocabulary bank just yet. I'm going to wait till we get the full unit circle, but it is going to be something to have memorized. It's the same thing as what we did above, just with a radius of 1.